All right, I'm going to do a quick recap of where we left off in the last class. We will go back a bit over back propagation that I finished in a hurry. So here's where we left off. We agreed that time series analysis must consider past inputs along with the current input, and if you want to look at the infinite past, you need recursion. We also saw that this can be done using some kind of state space model where we define a state that actually retains information about the past. The kind of architectures that we actually looked at. Yeah, we just have to,
Pinch.
that works. So here, the way we would do the training, we're going to perform back propagation through time. The reason we call it back propagation through time is that when you actually chart out the network is actually a feed-forward network. Although we call it a recurrent network, there is no self-recursion. When you actually consider how the input is processed, it's a strictly feed-forward network. Data comes in sequentially. You get outputs sequentially, so the entire network itself is a process that progresses through time and generates outputs through time. So the process of feeding forward actually goes forward through time. If we're computing derivatives, we know that we will be going backwards through the network. If you're going backwards through the network, you're going to go back from the end of time to the beginning of time. So this is called back propagation through time, BPTT. The way we would do it, we have a collection of training instances where each training instance is actually a sequence comprising a sequence of inputs and a sequence of desired or target outputs. And we also, for any current configuration of the network, thank you. For any current configuration of the network, we're going to have current output for the network. And we're going to actually define a divergence between the current output of the network and the target output when we perform our back propagation. So like all back propagation algorithms, you're going to have first a forward pass where we pass our data through the network, then pass the entire data sequence through the network. You'd get an entire sequence of outputs. And during back propagation, we're going to compute gradients backwards. So we would first compute our gradients out here and out here in the last column, then progress sequentially backwards and compute gradients through each column. Gradients will also get passed back through these arrows, which connect from the front to the back. So what we did in the last class, hurried through in the last class, we will spend a little more time this time around. But we're going to focus on one instance, and as I pointed out in the last class, we're going to sort of redraw the diagram just to ensure that the connections are clear, that we have a single output going both outwards and into the hidden unit at the next instant. Thank you. I got you? So we would define a divergence between the actual output of the network and the desired output sequence. So the divergence is not just a piecewise aggregate of or incremental aggregate of divergences at individual instance. It's a divergence between one sequence and another. Nevertheless, the divergence will be a function that we expect to be able to differentiate with respect to each of these outputs. So I can define the derivative of the divergence with respect to each of the outputs. And so here's where we stopped. At this point, we sort of rushed through stuff. Now today you're going to help me, which means if you don't help me, we're going to spend a lot of time on this slide. So let's be quick. Now, here again are there's a network with all the variables specified. So the inputs are x's. The hidden values are h of t. z1 of t is the affine input to the output activation. I'm assuming there's just one hidden layer. z0 is the affine input to the hidden activation. And these weights over here This weight, I'll call this W, well, whatever the weight is, we'll just come up with a notation as we write this down. So the way we are going to compute our gradients, the very first, we're going to start off at the very last column. A few rules. I'm going to be representing the derivative of the output with respect to any input as a gradient. With this, it's a Jacobian. I'll just be using the inverted triangle to represent it. The other one is that we also have this. If you have y equals w times x, then the gradient of any divergence with respect to w is going to be x times the gradient of the divergence with respect to y. These two are rules that we've defined earlier, so let me hold these two up here. So let's say I have defined my divergence with respect to y of t. When I'm computing my back propagation, performing my back propagation, I have the divergence over here. The next step is going to be the divergence at the input to this activation. So just using the standard chain rule, what would the divergence over there be? Anyone? What would the divergence at the input to the output activations be? Come on, speak up, because if you don't, I'm not going to write the next equation for the next 80 minutes. It's just the chain rule, right? So what would the divergence at the input of the, what would the derivative of the divergence with respect to the input to the final activation be? Considering that I've actually written the derivative of the divergence with respect to the output of the final activation. Just the chain rule, right? So give me the equation.
If suppose y equals f of z, then it should be f dash z into gradient y of z.
It's not f dash z is what would f dash z be? Are you speaking of a scalar derivative or a vector derivative? Scalar? The vector derivative, I'm writing this in vector form, right? I'm using gradients. So someone else want to help me? Actually, tell me what this is going to be. You've forgotten your name tags. So you're going to tell me what the next step is. What would the derivative out here be? Speak up, please. Pardon me?
Like dz over dy times.
These are vector derivatives. You cannot write these as dz over dy. We went through that a dozen times. Somebody else. Okay, actually you. So how would I write it if I wrote it properly? Okay?
Inverted triangle, then z.
I've actually shown, I have stuff up there, right? So what is that going to be? Inverted triangle, that is the Jacobian of what with respect to what? Complete it, please.
Z and y.
So this is the derivative of y of t with respect to z1 of t, right? Does this pre-multiply or post-multiply this particular divergence? It's a chain rule, right? So would that be to the left or the right? The NAR notation, you can't just multiply it on any side. Left multiply? Right, we were using the notation we had introduced. You actually answered a quiz question about this. I assume every one of you flunked that question. Right? Left or right? Vernon? Okay, because if it's not left, it's got to be right. Perfect, okay. This is beautiful. Sometimes the process of elimination really works, right? Okay, this is the derivative with respect to z, right? So what is the next derivative you would compute going backwards?
Wasn't this the formula we're trying to derive for the derivative of the divergence with respect to yt?
So this one is, the first one is the derivative of the divergence with respect to yt. So this was for yt, this was for z1t, right? So what would the next step be? You're going to be computing the derivative with respect to ht, right? So what is that going to be? So we are computing the derivative with respect to ht. What would that be? Pardon me? Post or pre? Post. Right? So this is going to be derivative of divergence with respect to yt times the derivative of yt. This is actually a Jacobian, correct? z1 of t times w. Now, there's a parameter over here, which is, let me call that w1, right? So what is the derivative with respect to w1? Look up there. So if I have y equals w times x, then the derivative of divergence, which is a function of y with respect to w, is going to be x times the derivative of divergence with respect to y, right? So now, given this, what would this derivative be just in that first column? Danish? Oh my, okay. Someone else? I'll spend all class on this. We're just going to get delayed in our schedule. So and considering that you're sort of sleeping through class, this is time well spent. Yes, Dhanendra? Divergence of z with respect to h, right? Z with respect to h. Times what? So that is, I'm computing the derivative with respect to w. Pardon me?
Everything else from 3.
Is that how it actually came out? No, I'm asking for the derivative of the divergence with respect to the weight that connects these two guys. What would that be? Look up here. Look at the formula up there, right? So what is that going to be? Yes.
H of t and the divergence of
H of t times derivative of the divergence with respect to
t. Oh, H of t. Wait, sorry, it's
z of t, right? So this is the derivative with respect to w1. This is the first parameter estimate we've got. First gradient we've got with respect to this parameter. Now, Min, you're going to help me for the next one, right? So if I'm performing back propagation, at this point, I've computed my derivatives with respect to this guy. I've computed my derivative with respect to this. I've computed my derivative with respect to this weight. I've computed my derivative with respect to h, which is the next derivative I would compute. Who said z0? Okay, so what would that derivative be? So this is with respect to z0. What is that derivative going to be?
Post-multiplied Jacobian
We're going to post multiply which one? Which term? I have several terms over here.
gradient of ht with respect to z0.
No, so the gradient of ht with respect to z0 of t. What does that multiply? Post multiply number 3, right? So derivative of divergence with respect to yt. I'm just writing the chain down. Yt with respect to z1 of t, and there's a w, right? Okay, so now what is the next step? So at this point we are now out here, right? So I'd like to compute the derivative with respect to this weight. What is that derivative going to be? Pardon me? X of t times the derivative of divergence with respect to what? z0 of t, right? Okay. So we've come down the first column. We've done the first column. There is another weight out here. This edge also has a weight. Let me call that W11, okay? So what is the derivative with respect to W11? Munira? Yes, what would that derivative be? She's going to answer me. Louder, please. We just have this. If I have any relationship of this kind, I've actually written what it's going to be, right? Okay, the next one. The next term's yours, right? So who was the one who said it? Christine, what was that? What is the derivative with respect to the weights on this edge? The derivative of the divergence with respect to the weights on this edge. And that's going to be h of t minus 1, right? Because that's the entrance times what? No. Jacobian z0 or the derivative of the divergence with respect to z0. That's not a Jacobian. This is going to be the derivative of the divergence with respect to z0 of t, right? So both of these are parameter updates. So note that we have all three of our parameter updates done. But all we've done is come down through the first column and considered everything through the last column and considered everything that goes through the last column. Now you're on the hook. So I'm going to start off at the next column. This is where things get interesting. So I'm going to assume that I've already got the, just to use up the space, I'm going to assume that I've already got the derivative of the divergence with respect to y of t minus 1. This is given to me, okay? Because that's how we have defined our divergence. So now when I'm going down the penultimate column, this term over here, what would the next term be? I want the derivative here, right? If I'm flowing down, going backwards, that would be the next term. So Sang, what would that be? Yeah, the t minus 1 column. You're working your way backwards. So that's the same as, that is okay, this is z1 of t minus 1 is going to be derivative of divergence with respect to y of t minus 1 times the derivative of y of t minus 1 with respect to z1 of t minus 1. This is going to be a Jacobian, correct? Just to remind you. Okay. So now things get interesting. What is the derivative? What is the next derivative you'd compute when you're going down that chain? Zenkai?
Calculate the.
Just follow this, right? So just tell me which term. I have a variable here. So if I'm going down, what is the next derivative I'll be computing? The derivative, okay, parameter update. What is that going to be? This is W1, right? What is this going to be? It is the number 4. Is it going to be exactly number 4? This is we said this got interesting at this point, right? So is it going to be exactly number 4?
H minus 1. HT minus 1.
But there's more than that. Yes.
It's going to be the sum of divergence.
Yes, we've already computed this particular derivative over here, right? It's a shared parameter network. Every column is exactly the same as every other column. Yeah? So this is going to be this term, which is equation 4, which is that term up there, plus, and what is this plus term going to be, Shankai? H, this is a plus, h t minus 1 times the derivative of z t minus 1. So you see what's happening over here. Because I have a shared parameter network, these things are getting accumulated, right? That is the magic of having repeated structure. Ronit, make sense? Okay. What is the next derivative I'd compute? Okay, the derivative with respect to h of t minus 1. What is that going to be? H of t minus 1 is going to be? Please explain.
So it's going to be similar to 3. We've got the divergence with respect to y of t minus 1.
Derivative of the divergence with respect to y of t minus 1 times derivative of y of t minus 1 with respect to z1 t minus 1 times w1. Okay. And are we done?
No, because that's all it also going to flow into the next.
Ah, yes. The output is going to 2 different places. Because the output is going to 2 different places, both of them are going to contribute to the derivative. So continue.
I'm not exactly sure what it would be. What is it?
I'm pretty sure you are. I'm pretty sure you're sure. Yeah, okay. So,
It's going to be a similar term, but with the t's rather than t minus 1.
so am I going to multiply it, add it? What? Add it. Okay, fine. Because there are 2 terms, right? And then what happens next?
Is it just the same as 3?
It is the which one are we doing?
The third equation on top of
The third equation is with respect to z prime of t, right? But that's not exactly what it's going to be. It's
It could be like the fifth equation.
It would be like the 5th equation. Can you tell me exactly what it's going to be? Okay, follow the chain, right? So Tobias.
So it's going to
derivative with respect to, okay, I can of the divergence with respect to y of t, okay?
Yeah, and then derivative of y of t with respect to
Y of t times the derivative of y of t, okay, with respect to z1 of t,
and there's going to be times w11.
w1, w11,
It's w11. And then derivative.
hang on. I think we're sort of we're getting stuck in the weeds over here. So let me help you, right?
Yes, please.
Okay, so I'm going to represent the derivative of the divergence with respect to z0 as this term here. I hope you can see this. I'm just going to call this derivative of the divergence with respect to z0 of t, okay? I'm giving you this term. Now help me out.
So it's just w11 times that.
w11 times, or is it the other way around?
I think the other way around.
Why think? You've got to be sure, right?
Visualize it in my head, right?
No, but we're going, as we go backwards, in our notation, you're always, which side are we multiplying?
We're
We're
post multiplying.
post multiplying, correct? So what would it be?
So it's going to be this times w11.
That's divergence of derivative of divergence with respect to z0 of t times w11. And everybody see why this happened? Okay?
Shouldn't be h. Why is it not h of t derivative with respect to h of t and z?
Well, pardon me?
The second term, why did we take a derivative with z0? Because the dependency is not on z0, it is on h of t, right? It is on z.
H of t, what happens between h of t and does h t minus 1 directly influence h of t, or does it influence z of t? What does it affect? It affects z of t, right? So you see what happened over here. As you followed your way backwards, you're basically, again, all of these are vector derivatives. These are not scalars, right? Meaning there are many of these, each derivative term actually represents many, many terms. And so, man, question?
Got totally lost where you
Where added
the second. Yeah.
the second term? Why have I added the second term?
Because you have another.
I have two things going out, right? So there's a derivative coming down each link. Because if I influence this, the way to think about derivatives is if I perturb this one little term, how many different ways is it actually going to affect the output? Right? And it's going to affect this through both connections. Make sense? Not quite. Not quite.
I
Okay.
get the part where you have to actually add it, but then why do you have to times the derivative of z0?
So this is, I'm looking at the derivative that's coming. So imagine this chain were not there. Imagine this connection were not there, right? What is the derivative of the divergence with respect to this guy? It's going to come this away only, correct? That's the derivative of the divergence with respect to this term times. Get it? Okay. It's kind of obvious once I actually point it out. That's why you need a sword. Now, okay. So, yeah.
So just to be clear, z0 of t is some weight times x plus some other weight times h of t minus 1.
Yes.
Okay, so cool.
So wait, z0, that's correct. Yes? Because z0 of t, no. z0 of t is not, yeah, it's a summation of both terms, right? Because you have inputs coming in from both ways.
Yeah.
Yeah. So this was the whole point of the self-recursion,
Yeah.
right?
I just wasn't sure if that's where they were.
Yeah, that was the point of the arrows, right? And again, this also clarifies something about the way we are representing things. Now continue helping me, right? Just for the joy of it. Now I want to what is the next term I would compute over here? Munira, what is the next term I would compute down the chain? Now you know, yes? Speak up loudly, please. So if I'm following my derivatives backwards, where have I currently stopped? I have stopped at h of t minus 1. What happens after h of t minus 1? The figure's there. So I'm currently out here. I'm currently out here. So I'm going to have to work my way back to this point, right? So what is that derivative? Derivative with respect to z0 of t minus 1. And what is that going to be? So this is the derivative of the divergence. Wait. You can actually refer to older equations, right? I've already computed the derivative with respect to h of t minus 1. Okay, now use that. Just the chain rule. Okay, Sanan, how would I do that?
Derivative of divergence with respect to ht minus 1. That's multiply by derivative of ht minus 1 with respect to
z0 of t minus 1. This is just a Jacobian, correct? That's all it's going to be, right? So we're just following the chain. Now the next step, I want to compute the derivative with respect to w0 at time t minus 1. What is that derivative going to be? So maybe you can help me now again. There's nothing like putting people on the spot for them to remember, get so traumatized that they remember this class forever, right? And so, please. You know the answer. Okay, Danish.
Well, we'd have to first add the derivative from
So this is which is going to be, that's equation 6, right? So this is E6 plus
plus x of t minus 1 times the divergence of
x of t minus 1 times the derivative of the divergence with respect to z0 of t minus 1. So you see how this is going. And the next time when I'm computing this derivative, that weight, because it's happened twice, I'm just adding stuff. Correct? And then there's one more thing, parameter I would like to compute the derivative with respect to, which is the weight on this edge. What is that going to be? Someone want to help me with that? Wait, no. Your turn's done. I know you can answer this. So Andrew, so what is the derivative with respect to W11 now? On this edge. So I've moved my way backwards. I've come here. What would that derivative be?
So the equation 7.
Equation 7 plus
the h
t minus 2, right? Divergence of z0 of t minus 1. And now, if I put you on the spot and give you many cups of coffee over the rest of the week, we'd work our way backwards. Right? But the equations are they're going to be exactly the same. You're going to go from t minus 1 to t minus 2, t minus 2 to t minus 3. The point I was trying to make with all of this is that when you're working your way backwards, two things happen. Anytime the output of a unit goes to multiple places, you're going to be adding these derivatives, number one. Number two, for the parameters themselves, the derivatives keep getting accumulated. Right? Make sense? So, and they keep getting accumulated because the parameters are shared. It's the same parameter every single time. So if I perturb this guy, I have to, whatever happens has to be added to whatever would happen if I perturb the guy in the next column. There are two independent columns. Yes, Dhanendra?
I have a question regarding the 10th equation.
Yes.
So when we're calculating with respect to W1, it's not feeding it from anywhere else.
No, it's not. So it's not W1 is a parameter. These are shared parameter networks. So think of it this way. There's a common W1 that is affecting both this edge and this edge, right? So we saw this. You're right? So if I change W1, both of them change. I've got to consider both of their, remember the influence diagrams we drew for these when we had shared parameter networks, right? So you have to keep adding these things up. And so you get this accumulation as you go over from the beginning end to the beginning, but every one of these is driven by a common divergence between one sequence and the other, and the ability to compute the derivative of the divergence with respect to each single y, right? And I can work my way backwards like so. Eventually, I can actually compute a derivative. Let's say I have the derivative of the divergence with respect to z0 of 0, right? What is the derivative of the divergence with respect to h of minus 1 going to be? I can see I get stressed out. What here? So there's one final derivative I must compute. So what is the derivative of the divergence with, can everybody see this portion of the board? Yeah. So what is the derivative of the divergence with respect to h of minus 1? I'm working my way backwards. Yes, Pulkit?
Derivative of divergence with z at time 0. Z1
Z0 equals derivative of the divergence is that Z0 at time 0, right? Z0 of time 0 times W11, right? So you can actually compute the derivatives even with respect to h of minus 1. At that last column, because you're not allowed to perturb h of minus 1, that there's no derivative to be added to the update for W11, right? But anyway, so you can work your way backwards and you can compute the derivative with respect to every single term in the network, with the caveats that anytime an output goes to multiple places, you have multiple derivatives being added. The derivatives for all of the weights are going to be added. And now that you know all of this, I don't need to show the rest of the slides. You know exactly what is happening in each of these. It's just a painful explanation of exactly what we just did on the board. And voila, we can actually compute the derivatives with respect to every single term in the network and eventually perform gradient descent to compute all of the parameters. And the gradient descent, now this is for only one training instance. If you had many training instances, all of these derivatives with respect to parameters are going to get added over the batch, and that is going to be the gradient that you're going to use to update your parameter values. But then we know exactly how to perform gradient descent. You've gone through this through your homeworks, right? So we've sort of established that it's actually fairly straightforward to perform gradient descent on this and to compute the derivatives. And you could do this for any of these architectures. We went through this for one, but this was only an illustrative exercise. I highly recommend that we not actually go through this exercise on paper for anything but the simplest architectures, and let your computers compute the derivatives for you, because there's so much, you need to know what the computer is computing. That's why you must go through this exercise. You don't want this to be a mystery. But then once you know exactly what's happening, it's easy enough to just let it take over. So for example, if I were trying to compute derivatives out here, this too is a feed-forward network, although I've represented it with a loop, right? When you go through time, you're going to compute stuff all the way to the end. This would also be a feed-forward network. You'd have a different, the same rules that we used out here are going to apply to compute the derivatives, and you would be able to learn these networks. And you can learn these parameters for pretty much any architecture, right? So there's one architecture, however, that doesn't strictly fall into this category. It's the bidirectional architecture, the so-called bidirectional recurrent neural network, originally proposed by Schuster and Paliwal in 1997. This is an interesting bit of work. They published it in ICASP, I think, in 1997. And nobody noticed it for a very, very, very long time. I mean, you had a few papers on and off. And then Alex Graves used it in his thesis for labeling sequences, and then suddenly realized, hey, bidirectional networks really work. And now the number of citations for that paper just has gone through the ceiling, because it's fundamental to pretty much everything we do these days. So how does this work? Now consider this. Just as the present predicts the future predicts the past, right? So the present predicts the future, because if I know what's happening now, I can tell you something what's going to happen in the future. But I can turn around, and I know that based on my current value, what must have happened in the past to cause me to happen, right? So it's basically everyone can predict children. They can predict their parents as well, right, in some sense. So this means I can actually try to capture influences both ways. Instead of trying to, if I'm trying, for instance, to perform a classification task, then I can look at it left to right, or if I'm trying to perform a prediction, right? If I want to predict today's stock values, I could predict it based on what happened yesterday, but the stock values tomorrow also tell me something about the stock values today. So I could actually go, I could go left to right or right to left in making my predictions. Why stay with one? Why not use both at the same time, right? So the bidirectional architecture does this. You have a forward layer where the information is fed forward, and you're making predictions as you go forward through time. Then you have a backward layer where you just flip the sequence left to right, and then you work on the flipped sequence and make predictions. And that's the equivalent of working backwards, starting at the end and working your way back to the beginning. Now each of these two is going to make a prediction. Instead of simply combining the predictions, you work off the hidden state values that each of these two have computed, and produce your final output based on both state values. So there are actually two distinct components to this network. There's a forward network, which processes inputs from 0 going forward to t. There's a backward network which processes inputs going from t back towards 0. And the way you would actually perform your predictions is that you would first pass your data forward through the network and compute all the hidden values, all the state values. You haven't yet computed the output. Then you're going to, once this is done, then you take the same data and work it backwards through the backwards network and predict the state values going backwards in time. So once you do this, you have the state values at each time computed both going backwards, forwards, and backwards. And then you can combine both of these to make your final output predictions, like so, right? So this is actually not complicated at all. Although the first time you draw it, it kind of looks complicated. When you look at how the process happens, it's very straightforward. And you can also see now how you can learn this network. Observe that there are no connections between the forward block and the backward block. So as far as the forward block is concerned, it's a strictly feed-forward network. As far as the backward block is concerned, it's a strictly feed-forward network looking from right to left. So you can actually perform your back propagation. So say you computed all of the variables and the forward pass, where you'd compute both the forward and backward networks in the final output. If you wanted to now update your parameters and learn this parameter using back propagation, as before, you define a divergence between the actual output and the desired output of the network. And then in the backward pass, first, since the output is independently influenced, since the hidden states for the two networks are independently computed, and the output and they're only connected through the output, you can actually look at the upper forward portion of the network and perform back propagation and compute gradients for the entire forward network. And then block that out and then perform back propagation, except in the case of back propagation for the backward network, you're going to go from the beginning to the end. And each of these are going to get their own gradients from the training instance. And these gradients are what you would use to actually update your parameters in a gradient descent network. gradient descent framework, right? So to summarize what we've done so far, this is where we should have been 49 minutes ago. It took a lot of time to extract that from you. Now, time series analysis must consider past inputs along with the current input again. And we use recurrent networks in order to be able to look at the infinite past. If you don't have recurrence, you cannot look through the infinite past. Now, training recurrent networks requires defining a divergence between the actual and desired output sequences and backpropagating. And you can train this by backpropagating gradients over the entire chain of recursion. And you'd actually be pooling the gradients with respect to individual parameters over time, as we saw on these slides. And then you can also do this bidirectionally, where you have one subnet going from the beginning of time to the end of time, the other one going from the end of time to the beginning of time. And they can combine their state values to make your predictions. So in these, backpropagation just follows the usual chain of recursions, going backwards for the forward network and going forwards for the backward network. Questions? So I'm actually going to skip directly to where I was supposed to be beginning. I'm kind of glad I went through that, because it was clear that, you guys have been dozing through all of this. So, and some of you are still dozing. Anyway, questions? Yes?
So we kind of talked a little bit about, like, there were different structures, like you could put in a sequence and then go through and output a sequence. Like, how would this change if you had a sequence input and a single value out?
Same thing. So we're actually going to see both of these in...
See different structures? Okay.
Yeah, we're going to actually see these different structures. And I don't think I'm going to finish all of these lectures in the time I allotted for them, or maybe I will. Maybe I'll just take an extra class, right? But we'll actually see how this works out. Yeah.
I'm trying to get into how the sequence length that we're predicting will affect the training length. If we have a bigger sequence length, then the gradient that we're accumulating for the initial time steps is higher. But is that
not so. Okay, we'll go over this business of what gradients are and how this is actually going to influence gradients, right? And this is the recurrent structures that people normally use these days are what are called long short-term memory networks, LSTMs. LSTMs are strictly and strongly in the field of magic and mystery, and nobody really knows how they work, but I'm going to give it a shot. But before that, any other questions? Yes?
So the distribution W11, is it always the same, or it's...
The point is every column, at each time step, the W11 value is exactly the same, right? You're just cloning the network.
But after this backpropagation, the W11 will get updated.
But you're aggregating everything. So then the underlying W11 value gets updated, right? And so that's going to get cloned everywhere again. It's a single structure. Always keep in mind that it's a single structure that keeps getting reused. So if you had to store the network, you're only going to store one structure. Make sense? Yeah. Okay. Now these networks, it turns out they're actually very powerful, as we just saw, right? Now, turns out recurrent structures can actually do stuff that non-recurrent structures cannot do. So we saw earlier that there are a couple of different ways of getting information from the past. You have this iterated structure, which is good for analyzing time series. This was a time delay neural network, right? You just looked at instead of just looking at the current input, you could look at the current and past several inputs and make your prediction. But we figured that if we want to look at the infinite past, the thing to do is to have recurrence, right? Turns out this is not the only thing that recurrent networks are good for. This is a very nice way of presenting this story, but they're actually much more powerful than simple flat structures. So let me give you an example, right? Let's say I want to train a little neural network, which is going to take two n-bit inputs, and it's going to produce a single n+1 bit output. This is just a standard network. How complex would this network be? This is a multi-layer perceptron that's actually performing addition, right? How complex would it be? We did this in class number 2. Anyone? Yes?
We need 2 or 3 perceptrons.
The input is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits, right?
Can you not convert it into decimal?
No, I want to do a bit addition, right? So this is actually going to be a fairly complex network, because if you want to do this with one hidden layer, you're going to have as many perceptrons. This is the truth table is going to be fairly complex, right? If I'm thinking of additions of inputs, I have 2n bits. Each of these 2n bits has an output, right? And so I'm going to have to define if I looked at the truth table, it's going to be fairly large. If I did this with one hidden layer, I'm going to have as many neurons as the number of blocks of inputs with the common output, as the number of rows in my truth table. I can even combine them, but the network is actually going to get, if I want one hidden layer, this network is going to have, the size of the network is going to be exponential in the size of the input. I could do this with more than one hidden layer, and it would get smaller. But it's not going to be simple, right? But I'm telling you, I can do this with one perceptron. Actually, with 3. How would I do it? Yes?
Would you have the output of the network being the addition, and then the recurrent part would be the carry bit?
Obviously, we are doing a lecture on recurrent neural networks, right? So there's a hint in the context. You're in a classroom where I'm talking about recurrent neural networks. How would you do this so here are the restrictions. Here, if I want to add to n-bit inputs, that network is going to be fairly large. And can it add an n+1 bit input? No, the input size is fixed, right? You're toast. Now, how would you do this with a recurrent network? Caleb? Just pass in one bit at a time, right? We can literally just do this like so. And that's about it. Previous carry, 1 bit each from each of the 2 inputs. It has 2 outputs. One is the carry, and one is the current output, right? And this network is going to have 3 neurons. 3, so it's 3 or 4, but it's going to be really small, right? And so not only is it very simple, it can actually add inputs of any size. So what you see is a recurrent structure is actually powerful enough to do some tasks that would take a static structure, many neurons, very simply with far fewer parameters. You can just learn to do it, right? So let me give you another example. The parity problem. I want to tell you if the number of ones in this input is even or odd. We've looked at exactly this problem before. What is this problem? Anyone who was here in lecture 2? Pardon me?
XOR.
This is just an XOR, right? If I'm just adding all the, this is just the parity is just the XOR of all of the input bits, right? So now if I want to compute the parity of an input, if I want to do it with an MLP, how many neurons would we need if we wanted to just have one hidden layer? Yeah?
I mean, didn't we say in the first lecture that in order to do an XOR, it would have to be infinite?
Exponential in the size of the input, right? So, but if I wanted to do it with multiple layers, how many would I need? Yeah.
I'm
represented in binary form, so shouldn't we just look at the last digit, see if it's 0 or 1?
No, I'm counting the number. It's a parity, so I'm counting the number of ones and zeros. Right?
Okay.
Right.
Numbers of ones.
Yeah, so is it even or odd? That's an XOR, right? So if I wanted to do it with more than one layer, how many neurons would we get? It's not was polynomial, it was linear. It was 3 per bit, right? So 3n. Or in fact, you could do it with 2n. That's what we saw, right? Anytime for every new bit, you're going to add 2 neurons for the XOR. So it's 2n. But then the network gets fairly deep. You're going to have log n layers, and it's complex. But then if I do this with a recurrent network, it's done with 2 neurons. That's it, right? I can actually do this parity check with just 2 neurons by using recurrence. I'm taking the first bit, XORing it to the next one, taking that output, carrying it over again, and now this can actually work on an input of any length. Okay? You're looking puzzled?
It takes some time.
Wait, where did I lose here?
Just how simplified this RNN unit can be.
This is it, right? I take the first bit, I XOR it with the next, take the result, XOR it to the next bit, take the result, XOR it to the next bit, and that's about it. I do this with just 2 neurons. Yeah?
Are you passing back those 1 and 0?
No, so this is the current input, this is the previous output, that's it. So this, if I just initially pass it 1 and 0, that output would go back with 0, that output would go back with 0, that output would go back with 1, and so on, right? I'm just passing the input 1 bit at a time and XORing it with the output for the previous bit. And the result that I get at the very end is going to give me the parity for my entire sequence, right? The number of parameters became really small, just 3, if I were learning this, or whatever 5 in this case, right? I just need 2 neurons. So we just saw that we took something that was really complex and drastic and shrank it down by using recurrence. So recurrent networks are actually much more powerful, or can be much more powerful than even flat structured static networks. And it's not just in problems where you're analyzing time series. This can be used in any kind of problems where the computation itself can be decomposed into a recurrent format. Everybody get it? Right? So now, we've seen that recurrent structures can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. We can use this to do this using backpropagation, but in all of this, I've shown a very simple recurrent structure, which is that every input, at every time, the computation depends on the state at the previous time. But there's nothing magical about that. The depth of the recursion can be arbitrary. You could have recurrence of this kind, where you're not only looking at the previous time, you're looking at 2 times in the past. If you're looking at 2 times in the past, the only distinction is that the initial values, you're going to have to define h for 2. You're going to have to define 2 h values, initial h values. You could look 3 time steps in the past. You'd have to define 3 h values. And all of the rest of the computation is going to follow exactly the same structure. You would have you can perform feed-forward computation. You can perform backpropagation exactly as we did for the simpler model, right? There is no restriction on any of this. So, how does this recurrence actually perform, right? What happens when you impose recurrence? Is it always nice and sweet and this is so beautiful? You can do all kinds of lovely computation. You can take the most complex computations, toss it at this, it's going to learn stuff, yeah?
We're going to have a problem with exploding derivatives because we're suddenly adding them up.
Yep. But it's going to, exploding derivatives will happen not just in recurrence, it happens anywhere. And we'll see this, right? But you can actually factor things down. The way to think about it is this one, is in this manner. Let me go back to my simple iterative structure, my time delay neural network, right? So I'm given in a time delay network or a convolutional structure, I'm giving you an input where I guarantee that every single input value is bounded, right? Is the output ever going to explode? Assuming my activations are not going to go to infinity for bounded inputs, right? Is the output ever going to explode? No. Why not? It's bounded. Okay, thank you, right? The surprise on his face was beautiful. Okay, so this is what we will call unless the input explodes, the output is not going to explode, right? And that is even if the activations, if all of them are, for example, rectified linear units, which means the output has the ability to go to infinity. If the input is bounded, the output is never ever going to just go off to infinity, because you're combining a fixed number of inputs, right? So because you're combining a fixed number of inputs, the output is kind of limited in the largest value it can take. This is what we will call BIBO stability, which is to say bounded input, bounded output stability. It's a highly desirable characteristic, and you would like your structures to be BIBO stable. If they're not BIBO stable, then the network, the structure that you have, cannot be depended on, because there's going to be some input that you feed it where the output just explodes and then everything goes haywire, right? So is this structure BIBO? Does this have the same property that if the input is always bounded, the output is always going to be bounded? Who said no? Why not?
Because your H factor could explode. It could grow across layers, and as a result cause, it's basically like making an output that's aggregating over time, and that way it could actually explode.
Yeah. So the short answer is yes. The long answer is it's a little more complex than that. If my activations are all sigmoids, will the output go to infinity? No, because the outputs of the activations are all bounded, right? But something else can happen. The output can just saturate, right? You can get to a point where it doesn't matter what else you feed into it, the output is going to be a constant maximum value. The network becomes perfectly useless, right? As far as we are concerned, there's really no distinction between the output exploding and the output saturating permanently. So BIBO stability is really, really required. Now, so in the case of linear activations, I'm going to start off with the simplest model. Let's assume that all of the activations are linear. What do I mean by linear activations? The output of any neuron is exactly the same as the affine combination that goes in. So we are not using a ReLU, we are not using a sigmoid, we're just using y equals z, okay? In that case, it's very easy to show that how the process becomes unstable. So we'll start off with that. Now consider this very simple linear activation case. So for the linear activation case, it turns out it's sufficient to analyze the behavior of the hidden layer, even in any case, regardless of whether the activation is linear or not. It's sufficient to analyze the behavior of the hidden layer, because the actual recurrence occurs only in the hidden layer. If the hidden layer explodes, the output explodes. If the hidden layer does not explode, the output does not explode. You're pretty much guaranteed, right? So let's just look at the hidden layer, and let's just assume a single hidden layer for simplicity. And I'm going to use the old torchlight effect, streetlight effect that we used way back when, that when it's dark, you go to wherever you can see. We've all seen this old joke. Some guy loses his keys in the bar, and the policeman finds him searching under a streetlight because, hey, what's the point of searching in the dark? You can't see anything anyway, right? So What we can analyze are linear networks. Linear networks are very easy to analyze analytically. If you begin analyzing networks with nonlinear activations, it gets fairly complex. So let's actually consider this guy. It's easier to analyze linear systems. And so we'll first look at some linear systems and we'll extrapolate everything to nonlinear systems. So in the linear system, the activations are all identity functions. We are only interested in what's happening in the hidden layer, because we've agreed that if we understand the behavior of the hidden layer, we sort of know how the network is going to behave. The zk at any time is some weighted combination of the hidden values at the previous time plus some other weighted combination of the input. And the output hk, because the activation is linear, is simply zk itself. So this is our very simple model, right? So how does the system actually respond? This equation looks kind of horrible, but maybe we can do this on the board and we will see. Who wants to help me? So the basic structure we had was this guy on top, right? WHK equals W, what did I write? WH HK minus 1 plus WX XK, where K represents time, okay? Now, I can write the hidden activation at time K in terms of the hidden activation at time K minus 1 and the input at time K, right? Can I write this in terms of the hidden activation at time K minus 2? Again, what is HK minus 1 expanded in the same way? So I can say HK equals WH. This thing can be expanded, can it not? So what would it be? That's going to be WH HK minus 2 WX XK minus 1 plus WX XK, right? Which, if I write this out, is going to be WH squared HK minus 2 plus WH WX XK minus 1 plus WX XK. Make sense? Right? I can go back and now write this in terms of XK minus 3. HK minus 3. If I wrote this in terms of HK minus 3, HK minus 3, what would it look like, right? So I just have to plug in HK minus 3 over here, right? So someone want to expand that for me? Anyone? I want to write that in terms of HK minus 3. So I want HK equals what?
WH squared, we just substitute.
That's WH squared times, so WH XK minus 3 plus WX XK minus 2, right? Okay. So plus whatever else we've got, which is WH X WX XK minus 1 plus WX XK. And that's simply going to become, somebody want to expand that for me? Yeah. Which one? Oh, that's H, I'm sorry. That's H, right? So someone want to expand that for me? Yeah. No, I want to expand HK, right? Write it out properly. Yeah. If I just expand it out, come on guys, someone help me. I've written it out here. Just okay, I'll do it. I know. It's getting to the end of class, so you're done. I'm not. I have no choice. Okay. Plus WH squared, WX, X, K minus 2, plus WH, WX squared, right? Is there a WX X squared? WH, WX, XK minus 1, plus WX, XK. So you can see how I can write this in terms of recursively in terms of previous values. And although the original equation is nice and tiny, right? What eventually happens is that I can keep pushing this hk minus 3 backwards. The next time if I write it in terms of hk minus 4, I'm going to be invoking xk minus 4, xk minus 3, xk minus 2, and xk minus 1. I mean, no, xk minus 2, 1, the past 4 values of xk, right? If I push the h that I'm considering one step more, I'm going to be incorporating one more x. So I can actually eliminate WH. I can eliminate h from this equation entirely. I can write the output entirely in terms of x's, right? And if I write it entirely in terms of x's, how many x terms am I going to find? All the x's to the beginning of time, right? Because so basically that's why you see this is an infinite memory system. That if I write it down in terms of inputs, I can write this down and it's going to invoke all the x's to the beginning of time. Correct? And specifically, here's what you're going to find. So you're going to find whatever. It's WH raised to xk minus 1 times the initial value. Forget this. It's WH raised to xk times WX times the first value of x plus WH raised to k minus 1 times WX times the second value of x plus WH raised to k minus 2 and so on, right? What is the key component over here? What would be likely to be causing the blow up? Two things. First, here's what you can say, you can do. If I know the response, so let's assume that I can define this response. This will just take a couple of minutes. As always, we'll run a couple of minutes over. So I have this initial value. And these are all going to outputs, right? Whatever the outputs might be, and all of them have inputs. So suppose I can write this term out, which is hk, I'll call this capital X, uppercase X, hk of xt. hk of xt represents the output at time k, yk, sorry, the hidden value, h of k, as a function of an input at time t. Okay, so hk of xt basically says, what would I get, what would this be if the only input I had was at time t? And you had everything else was 0, I had no other inputs, okay? So if I were to write it this way, here's something that interesting that happens. What you find is that the final output is the response of the system. I mean, it actually falls out of this, what is it, what is hk of xt, right? hk of xt is simply going to be this term times wx, right? That tells you the response of the system to an input at time t. So this guy is going to be, the output is going to be the, whatever happened because of this, plus whatever happened because of this, plus whatever happened because of this, plus whatever happened because of this. Basically, each new input is just adding, contributing additively to the output. And you can see that, you can actually see that from this equation, right? Each x is being transformed in some manner, and it's just being added to the output. So this means that if I analyze just this behavior tells me everything about how the system is going to respond. In fact, specifically, if I'm looking for long-term response, do things blow up or do things not blow up? All I need to really consider is what happens as a function of time when I have an input over here and everything else is 0. If I understand this behavior, I understand everything about whether the system is going to blow up or not. So I give it an input at time 0, is the thing going to blow up as time progresses, right? So can you shut your laptop, please? Right. This continues till the end of class. So this is basically what we are going to analyze. It's sufficient to analyze the response to a single input at time t equals 0 to know how the system is going to respond to the entire sequence of inputs, because it's going to have the responses to inputs at the different times just add up. So if I can guarantee that no matter how far out the system is not going to blow up, then regardless of the number of inputs, so long as the number of inputs is finite, the system is not going to blow up, right? So we just will look at the longest chain, and the longest chain tells us everything about it, and we'll look at this in the next class. Questions? Thank you.